All right, so taking a look at an SN2 reaction, and just taking a look at the mechanism. So what kind of reaction is this? This is a nucleophilic substitution that's bimolecular. Bimolecular meaning it has two star materials that are involved in the rate determining step. Nucleophilic because it involves a nucleophile. Substitution because you substitute one thing for the other. We're actually doing a substitution. So the mechanism will look like this, where you have two parts, you have a nucleophile and an electrophile. I added my lone pairs, they're not there already. First thing you want to do, we should number our carbons, 1, 2, 3. You could draw in any hydrogens you want to. Add in lone pairs, balance charges, all that good stuff. Find in each reaction, identify the nucleophile and electrophile. So in this case, it should be pretty easy to identify the nucleophile. The electron-rich part is going to be the chlorine, a lone pair of the chlorine. That means this molecule is the electrophile, but specifically it's on carbon 2. That's the most delta plus site because the iodine is pulling away electron density. That's the most polar bond, so carbon 2 is the electrophile. So we're going to show the electrons attacking carbon 2 from the nucleophile. At the same time, the carbon iodide bond breaks, and that would give us a new product with an I minus. Add in my lone pairs. Take a look, make sure I number my carbons correctly. 1, 2, 3. So I substituted iodine as iodine was we call these a leaving group. Substitute my leaving group with a nucleophile chlorine. And this reaction is a one-way street because if you took like a Cl minus versus I minus is more stable because it's larger and it can stabilize the negative charge because it has more electron orbitals. It's a larger atom. So another added layer to this to remember is, if you notice, this arrow is, I'm drawing this arrow in a particular way because I want to show that this chlorine is coming from the complete opposite side of where this carbon iodine bond is, 180 degrees away. That is because it's highlighting where the sigma star is at for that carbon iodine bond. If the bonding orbital looks like this is the sigma bond, where most electron density is around the iodine because it's more electronegative. The sigma star would be on the opposite side where electrons are not at, towards the less electronegative atom, in this case carbon. But notice they're 180 degrees apart. To break a sigma bond, to break any bond, you must put electron density into its antibonding orbital. So as these electrons from the chlorine go into the sigma star, which is 180 degrees away, you break the carbon iodide sigma bond at the same time. So that really does matter. Where sigma star is at really influences things, right? And it affects on how fast things react. So the more bulk you have here, right, the less likely it is to react. That's when we talked about the structure on the electrophile here. So this is a secondary alkyl halide. This is secondary. So it's getting pretty bulky and getting harder to make that reaction take place. If this carbon, so this carbon still has one hydrogen, that's why it's secondary. If it had no hydrogens, it'd be considered tertiary, and we would not be able to do this reaction. Tertiary, you can't do it because you can't get to sigma star. It's too hard. The electrons here bump into all the bonds off that carbon. So leaving groups in the SN2 reaction. So how good of a leaving group you have will affect how the reaction goes. So that's one way of thinking about that is how stable the leaving group is by itself. All right, so if you think about these leaving groups, how stable are they going to be? Which one's going to be more stable, I minus or F minus? Iodine is, just because it's larger and it can stabilize that negative charge. Right? So iodine would be, without thinking about solving, that'd be the more stable leaving group. Another way of thinking about leaving groups another type of way of doing it is also thinking about stability in this example I showed in class. What about these two? Which of these is going to be more stable? The carboxylate or the methoxide? And why? One of them is more stable than the other.
Isn't the carboxylate because it can do resonance and can spread out its charges?
That's right. The carboxylate can do resonance, which means, right, it can delocalize this lone pair. If you can do resonance, that means you can spread that charge out. Spread that charge out makes you more stable. And so this would be a better leaving group. Another way you can think about that's one way of looking at in terms of the products. Another way you could think about it is by thinking about the actual bond. It all comes here, the difference between iodine and fluorine is size. So we think about carbon-iodine bond versus a carbon-fluorine bond. Carbon and fluorine are closer in size, so they're going to have more orbital overlap than a carbon-iodine, right? If you remember, we think about the large size of iodine versus a smaller size of fluorine, and carbon, of course, is the same size. Right? How much orbital overlap determines the reactivity of your bond or lack thereof. So if you have less orbital overlap, that means you're a more reactive bond. So that also means you're a better leaving group because your bond is actually weaker too, more reactive. That's the other way of thinking about it, right? And you can kind of think about that with these two as well. This is easier. This one's easier, I think, just to look at the product and say that can do resonance. Where these two, you could look at both the product and at the start materials, the reactivity of the bonds. Now things get a little weird. Things will get a little weird in solvents. We'll talk about that later though. Right, so the result of all this means that if you're thinking about rate, right, so the rate of an SN2 reaction, SN2, the rate is equal to K times the concentration of the nucleophile times the concentration of the electrophile. Well, the more reactive the electrophile, right, or the better the leaving group, the more reactive this will be. So that's going to increase the rate. And so the type of electrophile matters, not just the concentration, right? This electrophile reacts faster than this one because it's a better leaving group. All right, so let's practice R or S here for the stereocenter. So first things first, let's make sure we know how to identify asymmetric centers. Carbon, sp3 hybrid, or it doesn't have to be carbon, it can be anything. That's sp3 hybridized and bond to 4 different things. So sp3 hybridized, bond to 4 different things. So it looks like there's bond to 4 different things, good. Now we have to rank these. That's the most important thing to do now. So the first thing, I like to either find the highest or the lowest. So the highest in this case will be the bromine, just based on atomic number, right? So let's make that red. That's 1. Now these might be a little trickier to find out which one's which. So carbon, 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 that's all tied up. So at this carbon, now we're playing war. It's bonded to a carbon, and a carbon. This one is bonded to a fluorine, a carbon, and a carbon. And up here we're bonded to an oxygen and a hydrogen and a hydrogen. Right, referring to this carbon, 2 hydrogens, oxygen, fluorine, 2 carbons, and 3 carbons. So who wins, or who wins this one? The fluorine one does. So that would be red, white. So that'd be white, be 2, white. Which one is going to be my next highest one? Which one's going to be the blue one? The oxygen one. 3 blue. And then the lowest one, the green, is 4 green. So now you need to take your model out. You need to have the green to your left, the white to your right, and the red coming at you and the blue going away from you. If that maps onto the right one, you grab the green ball, you turn it towards you, you say red, white, and blue. If it's red, white, and blue is rotating to the right, it's R. If it's rotating counterclockwise to the left, it's S. Which one is it? In this case, it is S. Biggest thing you need to be able to do is these rankings. That's what people get slipped up on usually. So let's take a look at 2-pentanol. It's like a sapling question. They say there's 2 possibilities of enantiomers for 2-pentanol. So make sure to understand what that means. That means 2-pentanol has an asymmetric carbon. So in this case, it has an atom that's sp3 hybridized bond to 4 different things, and that would be this carbon right here. So the way they have it drawn, at least the way I have it drawn, it's not RS right now, but it could be. I could ask you to draw it RS. It's of course also bonded to a hydrogen. Now, what they ask is, what would you expect differences between the 2 enantiomers, right? So if you have the R versus having the S. So enantiomers have, right, that's what these 2 would be to each other. They would be enantiomers. The stereocenters, the asymmetric centers are opposite. Everything's flipped. They're enantiomers. Enantiomers have the same physical properties. The example I used was my hands, our hands. Our hands are both mirror images of each other. They're enantiomers. They would have the same boiling point, the same melting point, right? But, right, so the same physical properties, they'd have the same TLC-RF, right? All that kind of stuff. They'd have the same IR, the same NMR we talked about. But when enantiomers, you can differentiate them when you think about enantiomers interacting with other enantiomers. So think about shaking hands with somebody else. My right hand needs someone else's right hand to really to actually make that work, that handshake work. Right? So your enantiomers can be differentiated. Enantiomers, pairs of enantiomers can be differentiated from each other when they're interacting with other enantiomers. Right? So think about shaking hands with somebody. Both had to have your right hands, or you both had to have your left hands to make that work. In your nose, in your bodies, you have receptors. That one enantiomer, the nose receptors in your body will interact with one enantiomer differently than the other. One enantiomer can make it smell like oranges. The other enantiomer makes it smell like lemons. And so enantiomers are different when they're interacting with other chiral molecules. And that's when you can differentiate enantiomers with other chiral molecules.